Hello everyone. In today's lecture we are going to study application of linear differential equations to electrical circuits. Already we have studied first order first degree differential equations and their applications to simple electrical circuits. In that we have studied LR and RC circuits which leads to first order first degree differential equation. But there are few circuits which leads to higher order differential equations, and a few of them we are going to study here. So let us see which are those circuits. In that, first one is LCR circuit. What is LCR circuit? So see this figure. L for inductor whose inductance is L henries. This one is capacitor whose capacitance is C farads. Resistor whose resistance is R ohms. So these are the three passive components which are connected in series with source of electromotive force, which is E volts. Current flowing through this circuit is I amperes. Also the charge, which is Q coulombs. So whatever here discussed, I have mentioned that thing here again. Hence, voltage drops across these three passive components. We know them. What are the voltage drop? So across the inductor, voltage drop is L di by dt. Here we have replaced this I by dq upon dt. That is, we know that current is rate of change of charge with respect to time. So I is dq upon dt, and we have replaced I by d square q upon dt square. So this is voltage drop across inductor. Second, across the capacitance, voltage drop is Vc is equal to 1 upon C integration I dt. See, because of this term, as we cannot solve this differential equation because of this integral sign, when we write the equation in the first order first degree differential equation, its application to electrical circuits, and that's why we needed to consider this circuit here in these higher order differential equations. Here we replace integration I dt by q and this C as it is. So voltage drop across capacitor is q upon C. Next, voltage drop across resistor is VR is equal to Ri. Again we replace this I by dq upon dt. So these are the voltage drops across these three passive components. Now, as capacitor is there, so depending upon initially whether it is charged or fully uncharged, depending upon that, later on we are going to obtain value of arbitrary constants, or we are going to obtain the particular solution that we will see in the example. Now, how to model this circuit? Okay, modeling means how to get the equation, how to express this circuit in the mathematical form, for which we must know very important law from electrical engineering, that is Kirchhoff's voltage law. Okay, so what is that? See the statement. So Kirchhoff's voltage law states that algebraic sum of the voltage drops around any closed loop is 0. In another way, it is also stated as algebraic sum of the voltage drops around any closed loop is equal to resultant electromotive force. So is using this law, mathematical expression of for the LCR circuit will be, so this is E is the voltage of the source. So E at inductor voltage get dropped. So total voltage in the circuit will get decreased. So therefore here added the minus sign. So E minus L d square q upon dt square. Then some voltage get drop across resistor. Therefore again decrease in voltage. Therefore it is minus R dq upon dt. And some voltage get drop across capacitor. So again there will be decrease in voltage, hence minus sign is added. So minus q upon C, and sum of all these voltage drops is equal to 0. So therefore we can rewrite this expression as, we will take all the negative terms to other side, and hence expression it becomes L d square q upon dt square plus R dq upon dt plus q upon c is equal to E. All the differential coefficients and the dependent variable, they are of degree 1, hence this is linear differential equation. Here highest order derivative is of order 2. Therefore, order of this differential equation is 2. L, R, C, they are constants and hence this is the linear differential equation with constant coefficients. And it can be solved using the methods that already we have studied. So using one of the methods, we can solve this differential equation. Solving it, we will be getting the charge and the current flowing in the circuit. So that is the solution of the given circuit. So charge and the current as a function of time. This is one thing. Second thing, as we know, when we solve the differential equations, we will be getting their arbitrary constants in the complementary function. Here, in case of the electric circuit, we want to obtain the particular solution for which we need the initial condition. So obviously in the problem, we will be giving the initial conditions, means at t equal to 0, how much is the current flowing in the circuit and how much is the charge in the circuit. Okay, so depending upon that values or the initial conditions, we can obtain values of arbitrary constants and hence particular solution to the given electric circuit. So this is LCR circuit. Next we are going to see LC circuit. In the LC circuit, we just have to remove the resistor from the previous circuit and then remaining all the things they are same. So this one is the circuit. Here only resistor is not considered, remaining all the things they are same. Voltage drop across inductor and the capacitor, they are L d square q upon dt square and q upon c respectively. Use Kirchhoff's voltage law, we will be getting mathematical expression like this. Simplifying it, we will be getting it as L d square q upon dt square plus q upon c is equal to E. Again we will solve it using one of the previous methods and hence we can obtain charge and current in the given circuit as a function of time, and using initial conditions we can obtain particular solution. Now we will go to solve the one example so that we will get the things what we have discussed here. So let us go to example. Example, an inductor of 0.5 Henry is connected in series with a capacitor of 0.02 Farad, a resistor of 8 ohms and a generator having EMF. So this is variable voltage source 80 into cos of 10t, where t is greater equal 0 and all they are connected in series. So what we want to do here, we want to find the instantaneous charge q and current I if I equal to 0 and q equal to 0 at t equal to 0. So see, this is the initial condition that when time t equal to 0, current and the charge they are 0, means we have been given here that the capacitor is fully uncharged as q is 0 at t equal to 0. Instantaneous means at a particular time t, at any particular time t, what will be the charge and current in the circuit. Indirectly, we want to obtain expressions for q and I as a function of t. So meaning of this instantaneous word. Okay, so now we will go to find out the solution. So first of all, we will again define this I and q. So I of t be the current, q of t be the charge in the LCR circuit at any time t. First of all, we will write down the given things. So given inductor L is of inductance 0.5 Henry, then capacitor uh, is of capacitance C, which is equal to 0.02 Farad. Then resistor is having resistance 8 ohms. Variable voltage source E is equal to 80 cos 10t volts. Okay, so these are the given things. Also, we have been given the initial conditions. Now, by Kirchhoff's voltage law, we will write down that differential equation for the LCR circuit, which is what? L d square q upon dt square plus R into dq upon dt plus q upon c is equal to E. Now, in this differential equation, we will replace the given values. So that will give us particular differential equation to the given circuit. So replace the values. Differential equation now it takes the form 0.5 d square q upon dt square plus 8 into dq upon dt plus q upon 0.02 equal to 80 cos 10t. Now divide throughout by 0.5, that is multiply throughout by 2. So this expression it becomes d square q upon dt square plus 16 dq upon dt plus 100q equal to 160 into cos of 10t. So see, this is the required linear differential equation with constant coefficients for the given electrical circuit. Now we want to solve this differential equation. So its auxiliary equation is which we are going to write down in operator form, which is d square plus 16d plus 100 equal to 0. Solve this differential equation. Roots are minus 8 plus minus 6i, which are complex roots with alpha equal to minus 8 and beta equal to 6. Hence, complementary function is, now see, as this differential equation is in terms of q and t, so we have to obtain solution for q, and hence here we have written our complementary function as qc, which is equal to e raised to alpha t. Alpha is minus 8, so e raised to minus 8t k1 cos of 60 plus k2 sin of 60. These k1 and k2, they are arbitrary constants whose value is supposed to be find. So this is complementary function. Now we want to find particular integral for q, which will be given by 1 upon phi of d of f of t. So phi of d is what? It is d square plus 16d plus 100, and f of t is what? It is 160, the right hand side function in the differential equation, which is 160 into cos of 10t. Now we know that how to solve this differential equation. See, as this cos is the trigonometric function, therefore we have to replace this d square by minus of 10 square. So which is what? Minus 10 square is minus of 100. Now replace d square by minus of 100. That will give us qp is equal to 1 upon minus 100 plus 16d plus 100, 1 upon 60 into cos of 10t. This 100 will get cancelled. We left with also this 16, 1 upon 60 divided by 16, then it will give us 10. So we left with 1 upon d 10 times cos of 10t. So this is 1 upon d is nothing but antiderivative. So this is simple integration like this. So it is 10 into integration of cos of 10t dt. Integrated, its integration is sine of 10t upon 10. So again 10 got cancelled and we left with qp equal to sine of 10t. See, in the particular integral we are not adding the integrating constant because those already we have added into the complementary function. So a qp particular integral is sine of 10t. Now, so this is qp, hence a solution for q, general solution is q equal to qc plus qp, which is e raised to minus 80 into k1 cos of 60 plus k2 sin of 60 plus sin of 10t. So this is the general solution for the charge as a function of time. General because here we haven't obtained the values of k1 and k2, arbitrary constants. Now we also want to obtain the current in the circuit at any time t. So what we will do? We will differentiate this relation q with respect to t. So let us do that. So q is this. Therefore, we call it as 1. Therefore, I is equal to dq upon dt. So differentiate this relation with respect to t. Expression is like this. So everyone knows how to differentiate any given function. To the first term we have applied the product rule of derivative. Second function is the simple function whose derivative is 10 of cos 10 into cos of 10 t. So this is the expression for q and I in and this is the general expression, but we want to find particular one. We call this expression as 2. To find the particular solution means we have to obtain the values of k1 and k2. So we will go to obtain that now. To find k1 and k2, we have to use the initial condition and then that values we have to put in these equations 1 and 2 and then we have to solve them. So given at t equal to 0, I is equal to 0, that is current is 0 and charge is also 0 at the initial stage. So we will put these values in 1 and 2 and we will solve them one by one. So when we put t equal to 0 and q equal to 0 in 1, that will gives us cq is 0, e raised to 0 is 1, cos 0 is 1, so k1, sin 0 is 0, so 0, and again sin 0 is 0, 0. So we got k1 equal to 0. Now we will obtain k2, for which we will put I equal to 0 at t equal to 0 in the equation 2 and that will give us I equal to 0 then minus 8. K1 is 0, so this term is 0, sin 0 is 0, so first term totally it becomes 0, then plus e raised to 0 is 1, sin 0 is 0 and cos 0 is 1, so here we got 6k2. Again cos 0 is 1, so we left with 10. So this is the expression and this gives us k2 is equal to minus 10 divided by 6. So that is value of k2. Now replace these values of k1 and k2 in 1 and 2. That will give us the particular solution and which are therefore q is equal to minus 10 by 6 which is 1.667 e raised to minus 8t sine of 60 plus sine of 10t. This one is the charge at any time t in the given circuit. Similarly, current I is equal to minus 13.3333 e raised to minus 8t sine 6t minus 6 into e raised to minus 8t cos of 6t plus 10 into cos of 10t. So this is the expression for the current as a function of time. That is the instantaneous current and the instantaneous charge. These are the approximate value. These first two terms in the current, they are the transient solutions and because of e raised to minus 8t term, it will soon it will becomes negligible, that is it becomes 0. Therefore, whatever the value of current, it will be given by only the steady state solution which is 10 into cos of 10t. So this is all about the given problem and the LCR circuit. In same way we can solve problem based on the LC circuit. I hope you understood this. Thanks for watching this video.